The moon is only about 239,000 miles, or 384,000 kilometers, from Earth. But near its south pole is a place colder than the surface of Pluto. Shackleton Crater is about 13 miles wide and roughly 2.6 miles deep. Its walls surround an interior where sunlight cannot directly reach large portions of the floor. The darkness does not pass. It does not disappear with sunrise. Some of the coldest permanently shadowed terrain near the lunar South Pole can fall below minus 400 degrees Fahrenheit, which is roughly minus 240 degrees Celsius, creating conditions unlike almost anywhere else in the solar system. And inside that darkness may be something extraordinarily valuable. Water ice for billions of years, molecules delivered by comets, asteroids, and other processes may have migrated into these permanent cold traps and remained frozen there. That ice could preserve a record of the solar system's past. It could also become a resource for its future, potentially providing water, oxygen, and even ingredients for rocket propellant. That is why the lunar South Pole has become one of the most important destinations in modern space exploration. The same darkness that may hold resources capable of helping humans travel farther from Earth also creates an environment extraordinarily difficult to enter, explore, and survive. Before we continue, if this type of content helps you relax, please give this video a like and subscribe to the channel. It helps this channel reach more people who love falling asleep to the sound of the universe. The story starts with a tiny tilt in the moon and the shadows it created billions of years ago. Everything begins with a subtle lean. When we picture worlds turning through space, it is easy to imagine broad seasonal swings like those we know on Earth. Our nearest neighbor behaves very differently. The moon tilts by only about 1½ degrees as it travels around the sun, while Earth is inclined by roughly 23½ degrees. That tiny difference shapes one of the most unusual landscapes anywhere in the solar system. From the lunar South Pole, sunlight never climbs high overhead. Instead, it skims the horizon at an angle so low that even modest ridges cast astonishingly long shadows. If a crater happens to be deep enough and its walls steep enough, those shadows never retreat. You can picture the sun circling endlessly around the horizon, always present, yet never managing to send direct light across the crater floor. Planetary scientists call these places permanently shadowed regions, meaning depressions that have remained beyond the reach of direct sunlight for immense spans of time. More than 40 confirmed examples exist around the lunar South Pole alone. Each one follows the same simple rule of geometry, yet every one preserves its own distinct history beneath an unbroken roof of darkness. As we move across this landscape, the surface becomes increasingly rugged. Countless asteroid and comet impacts have battered the South Polar region over billions of years, piling crater upon crater until the terrain resembles an overlapping record of nearly every major chapter in lunar history. Younger scars cut through older ones. Ancient rims crumble into newer basins. The result is the most geologically intricate region anywhere on the moon. Dominating this battered wilderness is the South Pole Aitken Basin, the largest and oldest confirmed impact basin in the entire solar system. It stretches for roughly 1,550 miles across and reaches depths approaching 5 miles. The collision that carved this enormous depression was so violent that many researchers believe it excavated rocks from deep within the moon itself, exposing material that would otherwise have remained forever hidden beneath the crust. Near the edge of this colossal basin rests Shackleton Crater. Its position is more than a coincidence of geography. Here, two extraordinary features overlap. One is the legacy of an ancient impact powerful enough to reshape an entire hemisphere. The other is the rare geometry that allows permanent shadow to exist. Together, they create an environment unlike any other place we have explored. When you step back and consider the broader picture, the arrangement feels almost improbable. A world with barely any axial tilt, a heavily cratered polar landscape, and one gigantic impact basin, all combine to produce conditions that could not easily exist elsewhere. We often think of the moon as simple and familiar because it hangs above us so often, yet its south pole reveals a landscape governed by precise celestial mechanics, where the smallest angle can shape billions of years of history. Long before Earth's continents settled into their modern shapes, an object wandered across the inner solar system on a collision course with the moon. It arrived during a violent chapter known as the Late Heavy Bombardment, a period roughly 3,600,000,000 years ago when countless remnants from planetary formation were still striking the young worlds. The moon preserved those encounters with remarkable fidelity, and one impact would reshape its south pole forever. The incoming body was likely several miles wide. Its speed reached tens of thousands of miles per hour, carrying an amount of energy almost impossible to picture. Within moments, the collision released a force comparable to billions of nuclear warheads exploding together. Rock behaved less like solid stone than flowing liquid. Material blasted outward in every direction before gravity slowly reclaimed it. As the surface collapsed inward, towering walls took shape around the fresh cavity. They eventually rose to nearly 14,000 feet above the crater floor, exceeding the height of any mountain in the contiguous United States. Nothing about those slopes was accidental. Their proportions and angles emerged directly from the physics of the impact, creating a structure whose geometry would influence every moment that followed. You can almost imagine the sun tracing its endless path around the lunar horizon, always approaching, never succeeding. Across billions of years, its light would skim the crater's rim again and again, yet the floor below remained beyond reach. The shape carved during a single instant became a permanent architectural feature of the moon, preserving conditions that almost no other place could sustain. The crater later received the name Shackleton, honoring the Antarctic explorer Ernest Shackleton. His expeditions across Earth's frozen southern frontier demanded endurance, careful planning, and persistence under relentless conditions. The lunar crater bearing his name reflects that same spirit of exploration, although its environment reaches far beyond anything encountered on our own planet. An invisible countdown also began with the crater's birth. Every wandering water molecule that drifted across the region gained a destination. So did traces of methane, ammonia, carbon dioxide, and other volatile compounds, meaning substances that evaporate easily under warmer conditions. Carried by comet impacts, asteroid debris, and interactions with the solar wind, these molecules gradually settled into the protected basin. Once there, escape became extraordinarily unlikely. The process unfolded with astonishing patience. Century after century, then million after million years, new material accumulated in layers while the surrounding moon continued changing through fresh impacts. The crater itself became less a scar than a vast natural archive, preserving tiny arrivals that would have disappeared almost anywhere else. Meanwhile, the rim experienced an entirely different existence. Several high points receive sunlight during more than 90% of the lunar year, bathing nearby ridges in repeated illumination while the floor remains untouched. Across only a few miles, one location spends nearly all of its time in sunlight and another receives none at all. We rarely encounter such dramatic environmental contrast on a single planetary landscape, yet here it emerged from one ancient collision whose consequences have endured ever since. Imagine trying to warm your hands beside a fire that does not exist. That simple absence captures the defining physics of Shackleton's floor. Cold alone is not unusual in the solar system. What makes this place extraordinary is the complete failure of nearly every natural source of heat that we normally take for granted. Even the coldest deserts and polar regions on Earth are constantly exchanging energy with their surroundings. Heat rises from deep within the planet through geothermal activity. Air carries warmth from one region to another. Nearby mountains and valleys emit invisible infrared radiation, a form of thermal light produced by warm objects. Every landscape participates in an endless conversation of energy moving from place to place. None of those exchanges operate inside this crater. The moon's interior contributes almost no measurable geothermal warmth here. There is no atmosphere to circulate heat across the surface. The surrounding walls are themselves so cold that they radiate only the faintest trace of thermal energy toward the basin below. Instead of balancing temperatures, the environment steadily loses whatever little warmth reaches it. Physicists describe such a place as a thermodynamic dead zone, meaning a region where incoming heat is so scarce that energy continually escapes faster than it can be replaced. The crater floor settles into a remarkable state of equilibrium, remaining frigid through the simple absence of replenishment. Nothing actively cools it, almost nothing warms it. Average temperatures hover near negative 333 degrees Fahrenheit. Some measurements suggest pockets falling to roughly negative 413 degrees Fahrenheit. Those values place Shackleton astonishingly close to absolute zero, the theoretical limit at negative 459.67 degrees Fahrenheit, where molecular motion reaches its lowest possible energy state. Nature cannot actually descend below that boundary, making this crater one of the nearest natural approaches known anywhere in the solar system. At temperatures like these, familiar substances behave in unfamiliar ways. Nitrogen freezes into solid form. Oxygen also freezes. Carbon dioxide hardens as well. Molecules drifting across the lunar surface eventually encounter conditions where movement almost ceases, allowing them to remain trapped for extraordinary lengths of time. You can think of the crater as an enormous natural freezer operating without electricity, machinery, or maintenance, relying only on geometry and time. Human technology struggles against such extremes. A person standing on the crater floor would continuously lose heat through radiation, the process by which warm objects emit energy into colder surroundings. Every layer of insulation would work relentlessly to slow that escape, yet the surrounding environment would continue drawing energy away. Current lunar exploration suits developed by the National Aeronautics and Space Administration are engineered to protect astronauts in temperatures reaching approximately negative 251 degrees Fahrenheit. Shackleton's coldest measured regions descend roughly 83 degrees farther. That difference represents far more than discomfort. It pushes beyond the operational range for equipment intended to support human life, illustrating how this crater challenges engineering with the same patience that shaped its frozen landscape across billions of years. Picture a single water molecule drifting across the moon. It has no map, no destination, and no atmosphere to carry it. For ages beyond ordinary imagination, it wanders in short leaps across the surface until chance delivers it into one remarkable place. Once it arrives, the journey is effectively over. Planetary scientists call such a destination a cold trap, meaning an environment so cold that volatile compounds, substances that would normally evaporate with modest warming, become frozen and remain in place. Water is one example. Methane behaves the same way. Ammonia does as well. Carbon dioxide also becomes locked into the frozen landscape when conditions remain cold enough for long enough. Among every known cold trap on the moon, Shackleton stands apart. Its exceptional depth, broad interior, and uninterrupted history of darkness have allowed it to preserve material for more than 2 billion years. Other permanently shadowed craters also collect frozen compounds, yet few combine these favorable conditions with such remarkable stability across geological time. Each comet striking the lunar south polar region contributed more than broken rock. Many carried water ice together with other volatile ingredients formed during the earliest stages of the solar system. Some of that material scattered across the surrounding terrain after impact. Tiny particles and individual molecules gradually migrated away from their original landing sites until gravity and temperature guided them toward the crater floor, where departure became exceedingly unlikely. The sun contributed as well, although in a very different form. The solar wind, a continuous stream of electrically charged particles flowing outward from the sun, constantly bombards the lunar surface. Many of those particles are hydrogen atoms. When hydrogen encounters minerals containing oxygen within the lunar soil, chemical reactions can produce new water molecules directly on the moon itself. Those newly formed molecules do not remain fixed forever. They travel through a process called thermal migration, meaning they repeatedly warm, lift away from the surface, settle elsewhere, then repeat the cycle. Over countless repetitions, they naturally move from warmer regions toward colder ones. Given enough time, many eventually arrive inside a permanent cold trap where the cycle ends because there is no longer enough heat to send them onward. You can think of Shackleton as an enormous natural archive assembled one molecule at a time. Its ice has neither melted nor substantially evaporated for more than 2 billion years. Every frozen layer preserves a tiny fragment of the environment in which it formed, creating a physical record far older than any landscape remaining on Earth. Researchers believe these deposits may be stratified, meaning arranged in distinct layers, much like pages within a history book. One layer could preserve the aftermath of an ancient comet. Another may record debris from a different impact, separated by millions of years. Read carefully. Those frozen pages could reveal how the inner solar system changed across immense stretches of time, preserving events that disappeared almost everywhere else except within this enduring reservoir beneath Shackleton's unchanging shadow. The search began with an unusual challenge. Scientists were trying to study a landscape that refused to reveal itself through ordinary observation. Cameras depend on reflected light, yet the most intriguing regions near the lunar South Pole offered none. For many years, the possibility of frozen water remained an elegant hypothesis supported by physics rather than direct evidence. A breakthrough arrived in 1994 with a spacecraft called Clementine. Among its experiments was a technique known as bistatic radar, a method that transmits radio waves toward a surface and studies how those signals return after bouncing back. Unlike visible light, radio waves can provide clues about the physical properties of terrain, even when ordinary photography cannot. The echoes coming from the South Polar region displayed unusual patterns that matched what researchers expected from buried or mixed water ice. The findings generated excitement, although they stopped short of certainty. Other materials could sometimes produce similar radar signatures, leaving room for debate. Scientists had taken an important step, yet the mystery remained open. More evidence would be needed before anyone could confidently describe the hidden contents of those permanently shadowed landscapes. Another piece of the puzzle appeared in 1998 with the arrival of Lunar Prospector. Instead of relying primarily on reflected radio waves, this spacecraft measured hydrogen distributed across the moon. Hydrogen is one of the essential ingredients of water, making unusually high concentrations a valuable clue. Both lunar poles showed significant enrichments, suggesting that frozen water could indeed be stored within their enduring cold traps. The strongest confirmation came more than a decade later through an experiment that seemed surprisingly destructive. On October 9th, 2009, the National Aeronautics and Space Administration intentionally directed the Lunar Crater Observation and Sensing Satellite Impactor into Cabeus Crater, another permanently shadowed region near the lunar South Pole. A second spacecraft followed behind, watching the expanding plume of debris with scientific instruments as material burst upward into sunlight for the first time in countless ages. What emerged transformed planetary science. The cloud contained unmistakable evidence of water ice. It also revealed carbon dioxide, methane, ammonia, hydrogen sulfide, and even ethanol. Rather than preserving only frozen water, these polar cold traps had accumulated an unexpectedly rich collection of volatile compounds originating from comets, asteroids, and interactions with the solar wind across immense spans of time. The impact altered scientific thinking with remarkable speed. Researchers no longer viewed the lunar South Pole as merely an exceptionally cold environment. They recognized it as a chemically diverse reservoir holding materials of enormous scientific and practical value for future exploration. Attention naturally returned to Shackleton. The Lunar Reconnaissance Orbiter has spent years examining the crater using radar, laser measurements, and other remote sensing instruments capable of studying terrain beyond the reach of ordinary cameras. Those observations have revealed surface ice deposits, refined maps of the crater's shape, and strengthened the growing picture of a place whose greatest discoveries emerged only after scientists learned how to investigate a world they could scarcely see. Some places reveal themselves the moment a camera arrives. Shackleton demanded an entirely different conversation. For scientists, the challenge was almost paradoxical. How do you create a detailed map of a landscape that almost never reflects enough light to photograph in any ordinary sense? The answer required instruments that could measure distance, texture, and composition without depending on sunlight at all. The Lunar Reconnaissance Orbiter lifted away from Earth on June 18, 2009. Since entering lunar orbit, it has spent years surveying the moon with extraordinary precision, producing the most detailed maps ever assembled of our nearest celestial neighbor. Every pass added another layer of information, gradually transforming regions once known only through rough outlines into landscapes measured with remarkable accuracy. Shackleton remained among the greatest challenges. Pointing a conventional camera into its interior accomplished very little because there was almost no natural illumination to reveal the terrain below. The crater demanded tools capable of sensing features that ordinary photography could never record. One of those instruments was the miniature radio frequency radar system. Rather than collecting visible light, it transmitted carefully measured radar pulses into permanently shadowed terrain and analyzed the returning echoes. Different materials reflect radio waves in different ways. The patterns returning from Shackleton matched expectations for water ice mixed within the surface, strengthening evidence gathered through earlier missions while providing much finer detail about where those deposits might exist. Another remarkable instrument approached the problem from an entirely different direction. The Lunar Orbiter Laser Altimeter repeatedly fired laser pulses toward the surface, measuring the tiny interval before each pulse returned. By calculating those travel times with extraordinary precision, scientists constructed a detailed, three-dimensional model of the crater. The method required no sunlight because the spacecraft supplied its own brief flashes of laser light, allowing hidden topography to emerge point by point. Those measurements revealed an unexpected landscape. Considering the crater's immense age, researchers anticipated a rough interior shaped by countless impacts. Instead, the floor appeared unusually smooth and relatively flat. One possible explanation is that frozen material gradually accumulated across billions of years, softening smaller irregularities and creating a more even surface than bare rock alone would produce. The crater walls offered another intriguing clue. Their reflectivity proved greater than that of the floor beneath them. Such observations remain consistent with patches of exposed or near-surface ice clinging to steep interior slopes where material delivered by ancient impacts may have collected and persisted under enduring cold conditions. A remarkable milestone arrived in 2023. A highly sensitive camera called ShadowCam, carried aboard the Korean Pathfinder lunar orbiter, succeeded in capturing the first direct images of Shackleton's interior using only faint earthshine and distant starlight. Even those minimal sources of illumination became enough for an instrument designed specifically for extreme darkness. The resulting views showed a landscape almost stripped of familiar visual landmarks. Broad stretches appeared level and remarkably featureless. Across spans of time exceeding the existence of complex life on Earth, the crater floor has changed very little, preserving a scene that modern technology could finally observe after wading through billions of years beyond ordinary sight. For years, the most important question was whether frozen water existed at all. Today, the conversation has shifted toward something far more practical. How much is actually there? The answer remains uncertain, yet even the most conservative estimates describe a resource of extraordinary scale hidden within the moon's permanently shadowed regions. Current scientific studies suggest that the permanently shadowed craters surrounding the lunar South Pole together may contain anywhere from roughly 100 million to 1 billion tons of water ice. That broad range reflects the difficulty of measuring deposits that remain inaccessible beneath enduring darkness. Remote sensing instruments can identify strong evidence of ice, but only future exploration will determine exactly how much lies beneath the surface. Shackleton itself is believed to contain hundreds of millions of pounds of frozen water. Researchers continue refining those estimates because no spacecraft has yet landed on the crater floor to drill, sample, and directly measure the deposits. Every new observation narrows the possibilities, yet the complete picture still waits beneath layers of ancient frozen material. Large numbers often lose meaning without comparison. Imagine 100 million tons of water gathered into a single reserve. That amount equals roughly 40 billion gallons. Such a supply could provide water for a city of 1 million people for approximately 80 years. Yet volume alone does not explain why scientists and engineers pay such close attention to Shackleton. Its greatest value comes from location. Every pound of cargo launched from Earth toward the moon demands enormous amounts of fuel, engineering, and expense. Delivering useful materials all the way to the lunar surface has historically cost around $10,000 for each kilogram transported. Water already waiting on the moon eliminates the need to carry every gallon across nearly 250,000 miles of space. Once extracted, frozen water becomes one of the most versatile resources available to future explorers. It can be purified for drinking. It can support agriculture inside carefully controlled habitats. Thick reservoirs of water also provide valuable protection against space radiation because water absorbs a significant portion of the energetic particles constantly arriving from the sun and deep space. Perhaps the most transformative application involves transportation itself. Water can be separated into hydrogen and oxygen through electrolysis, a process that uses electricity to split water into its constituent elements. Hydrogen serves as an exceptionally effective rocket fuel. Oxygen acts as the oxidizer required for combustion in the vacuum of space. Together, they form one of the most powerful chemical propulsion systems ever developed for spaceflight. Viewed from that perspective, Shackleton becomes more than a scientific destination. It becomes infrastructure, a reliable operation producing water, oxygen, and rocket propellant at the lunar South Pole could allow spacecraft to refuel without returning to Earth, dramatically changing how future missions are planned. Journeys toward Mars, expeditions into the asteroid belt, and voyages even farther outward all become easier when the first major supply depot already exists beyond Earth's gravity, preserved for billions of years inside one remarkable crater. Stand on the rim instead of the floor, and the entire character of Shackleton changes. Only a short distance separates these two environments, yet they belong to completely different worlds. Below lies a basin where sunlight never reaches. Above, certain ridges spend almost the entire lunar year illuminated by the sun, creating one of the most remarkable contrasts found anywhere beyond Earth. These elevated locations are known as peaks of eternal light, a name given to mountaintops and ridges that receive sunlight during the overwhelming majority of the lunar year. They are not illuminated every single moment, yet some remain in sunlight for more than 90% of that time. Such consistency is extraordinarily rare on the Moon, where most locations endure long periods without solar energy. For engineers planning humanity's return to the lunar surface, that difference changes nearly everything. Reliable electrical power has always been one of the greatest obstacles to establishing a permanent outpost. Solar panels placed on one of these elevated ridges could operate through almost the entire year, reducing dependence on massive batteries or alternative power systems that must survive lengthy periods without sunlight. The geography adds another remarkable advantage. Shackleton's rim rises roughly 14,000 feet above the crater floor, providing an elevated position with a nearly direct view into the permanently shadowed interior below. From that height, explorers could oversee equipment operating in conditions that remain among the coldest known anywhere in the solar system, while keeping most of their own infrastructure in continuous sunlight. You can imagine a practical arrangement emerging from that landscape. Power stations, communications, equipment, and living quarters occupy the bright rim. A cable system or rail network extends downward into the frozen basin, transporting machinery, supplies, and eventually extracted ice back toward the surface. Electricity generated above could flow directly to mining equipment below, linking two completely different environments into a single working system with remarkable efficiency. This combination of abundant sunlight and accessible frozen resources explains why the region has become central to modern lunar exploration. The National Aeronautics and Space Administration selected the lunar South Pole as the destination for the Artemis program, which seeks to establish a sustained human presence on the Moon rather than brief visits lasting only a few days. In 2022, the agency released a map identifying 13 candidate landing regions for the Artemis 3 mission. the planned first crewed lunar landing since Apollo 17 departed the moon in 1972. Most of those candidate locations cluster around the rim of Shackleton and neighboring terrain, reflecting years of scientific analysis and engineering studies focused on the unique advantages offered by this landscape. Interest extends well beyond a single nation. China's lunar exploration program has also concentrated significant attention on the South Polar region. The European Space Agency, the Japan Aerospace Exploration Agency, and the Indian Space Research Organization all have missions planned, operating, or under development that contribute to understanding this extraordinary frontier. Without drawing much public attention, the rim of Shackleton has become one of the most strategically important destinations beyond Earth, where science, engineering, and international ambition now converge upon the same narrow band of illuminated ground. Radiation is often imagined as something arriving in straight lines from distant space. Around the moon, that picture is only part of the story. Every moment, invisible particles stream across the solar system from the sun and from far beyond our galaxy. Earth is protected by a thick atmosphere and a powerful magnetic field that deflect or absorb much of this relentless bombardment. The moon possesses neither safeguard. An unprotected person, standing on the open lunar surface, would receive a radiation dose roughly 200 times greater than someone at sea level on Earth. During extended missions, that exposure becomes a serious concern for both human health and sensitive electronics. Every habitat, vehicle, and spacesuit intended for long-term exploration must account for this constant flow of energetic particles. At first glance, Shackleton seems to offer an advantage. Its towering walls block large portions of the surrounding sky, reducing exposure from particles arriving near the horizon. If radiation came only in direct paths, the crater might appear naturally sheltered. Yet the lunar environment introduces another layer of complexity that cannot be judged simply by looking upward. The surface itself becomes part of the problem. High-energy cosmic rays striking the lunar regolith, the blanket of loose rock fragments, and dust covering the moon trigger cascades of secondary particles. These include neutrons and gamma rays, forms of radiation capable of penetrating deeply into surrounding materials. Instead of stopping with the initial impact, the incoming energy is transformed into new radiation emerging from the ground itself. Within a deep crater, that process becomes especially interesting. Some secondary particles travel outward until they encounter steep walls, where additional interactions scatter them in different directions. Rather than creating a straightforward radiation field like the open plains nearby, the crater may produce a more complicated environment shaped by its own geometry. Researchers continue studying exactly how these interactions unfold because detailed measurements from the crater floor remain limited. Water ice may provide part of the solution. Hydrogen is among the most effective natural materials for slowing energetic particles, which explains why hydrogen-rich substances are frequently incorporated into spacecraft radiation shielding concepts. Ice containing abundant hydrogen could therefore help reduce portions of the secondary radiation reaching equipment or future habitats if incorporated thoughtfully into their design. The frozen deposits may also preserve another challenge. Across billions of years, cosmic rays have continuously altered the uppermost layers exposed to energetic radiation. Computer models suggest that this prolonged bombardment may have created a thin blanket of chemically modified material above the cleaner ice beneath. Complex compounds produced through radiation-driven reactions could become mixed with dust and frozen volatiles resting at the surface. That possibility changes how future mining operations may proceed. Engineers may need to remove and process the upper layer separately before reaching the purer ice stored below. We often picture lunar ice as a resource waiting to be collected, yet the environment has been reshaping its surface continuously across immense spans of time. Even here, where the cold has preserved so much of the past, radiation has quietly continued writing its own subtle chapter into the landscape. The moon often appears completely unchanged from one night to the next. Its craters seem permanent, its plains unaltered, and its horizon fixed beyond ordinary timescales. Yet, beneath that familiar appearance, the ground still moves. The motions are subtle, infrequent, and profoundly different from the earthquakes experienced on Earth, but they remind us that the lunar surface remains an active world. Scientists recognize four distinct kinds of moonquakes. Deep moonquakes originate hundreds of miles beneath the surface, driven largely by gravitational stresses as Earth gently flexes the moon during its orbit. Shallow moonquakes occur much closer to the surface and release considerably greater energy. Meteorite impacts produce another category as incoming space rocks strike the lunar landscape. Finally, thermal quakes develop when the ground expands and contracts during the dramatic temperature changes that accompany lunar sunrise and sunset. Among these, shallow moonquakes present the greatest concern for future explorers. Some have reached magnitudes of approximately 5 and 1/2 on the Richter scale. That strength alone is significant, yet their duration makes them especially unusual. A similar earthquake on Earth often lasts around half a minute before fading. On the Moon, comparable shaking can continue for as long as 10 minutes. The explanation lies beneath the surface. Earth's crust contains abundant water and fractured rock that gradually absorbs seismic energy as it travels outward. The Moon is far drier and considerably more rigid. Seismic waves encounter fewer opportunities to lose energy, allowing them to reverberate through the interior for remarkably long periods. Rather than fading quickly, the entire body of the Moon behaves much like a struck bell, carrying vibrations long after the initial event. Evidence for this surprising activity came directly from the Apollo missions. Between 1969 and 1977, astronauts left sensitive seismometers on the lunar surface. Those instruments continued operating for years, recording thousands of moonquakes across many regions. The data revealed that the moon was far from geologically dormant, providing scientists with the first detailed record of its continuing internal activity. For engineers considering a permanent settlement near Shackleton, these discoveries carry practical consequences. The crater rim rises steeply above the frozen basin, while many slopes consist of loose regolith, the blanket of fragmented rock and dust covering the lunar surface. Prolonged shaking could gradually destabilize portions of those slopes, increasing the likelihood of rockfalls or landslides where future infrastructure might be constructed. Recent research has reinforced that concern. In 2023, scientists reanalyzed the historic Apollo seismic records using modern techniques and found evidence suggesting that the lunar south polar region remains associated with active fault systems, fractures within the crust where blocks of rock have shifted over time. The landscape surrounding Shackleton, therefore, cannot be treated as perfectly motionless across decades of occupation. Every proposed structure must account for that reality. Habitats anchored to the rim, solar power installations, and communication towers would all require designs capable of enduring repeated shaking. Any cable or rail system descending toward the crater floor would face additional challenges as vibrations traveled through supporting structures over many years. Even on a world that seems timeless from afar, successful exploration depends upon respecting a landscape that still possesses the ability to move. Long before anyone reaches the frozen deposits beneath Shackleton, another obstacle waits at the surface. It weighs almost nothing. Individual grains seem insignificant, yet together they have challenged every crew that has ever walked on the moon, turning ordinary movement into an engineering problem that begins the instant a spacecraft touches down. This material is called regolith, the blanket of fragmented rock and dust covering the lunar surface. Unlike sand on Earth, it has never been rounded by flowing water, softened by wind, or broken down through familiar weather. Instead, it represents the accumulated result of roughly 4.5 billion years of meteorite impacts, each collision shattering solid rock into progressively finer fragments, while leaving sharp edges almost perfectly preserved. Viewed under a microscope, lunar dust appears remarkably hostile. Individual particles are jagged, irregular, and capable of locking onto surfaces through electrostatic charge, the buildup of electrical attraction created as particles exchange electrons. The dust clings stubbornly to metal, fabric, glass, and machinery. It scratches exposed surfaces, works its way into moving components, and resists efforts to brush it away. The Apollo astronauts experienced these problems after spending only brief periods on the moon. Dust collected inside suit joints, increasing wear on seals designed to protect them. Helmet visors accumulated fine scratches that reduced visibility. Equipment filters became clogged. Once back inside the lunar module, small amounts of dust entered the cabin atmosphere, irritating eyes and airways. Several astronauts reported symptoms resembling allergic reactions after accidentally inhaling the particles. Buzz Aldrin later offered an especially memorable description. As the dust encountered moisture inside the cabin for the first time in its existence, chemical reactions occurred on its freshly fractured surfaces. He said the resulting odor resembled wet ashes, an unexpected reminder that lunar material behaves differently once introduced into an environment containing air and water vapor. Conditions within Shackleton may present an even greater challenge. Scientists expect dust preserved inside permanently shadowed regions to possess unusually strong electrostatic properties because those particles have remained isolated from sunlight-driven chemical changes for immense spans of time. Their surfaces may therefore behave differently from regolith collected during the Apollo missions, although direct measurements still await future exploration. Landing there introduces another complication. Rocket engines generate powerful exhaust plumes capable of blasting loose regolith across considerable distances. A spacecraft descending toward the crater floor could throw dust onto nearby instruments, cover reflective surfaces, and contaminate the very ice deposits researchers hope to study in their original condition. Every landing, therefore, becomes both an arrival and a disturbance. Engineers have proposed several ways to reduce these effects. Future missions may establish dedicated landing zones positioned away from sensitive scientific sites. Robotic systems could prepare the surface before larger spacecraft arrive, stabilizing loose material. Instruments may also be placed where prevailing exhaust patterns are least likely to reach them during descent. These concepts appear promising, yet none has been tested operationally within the unique environment surrounding the lunar South Pole. When the first spacecraft finally settles onto Shackleton's floor, it will encounter dust that has remained untouched since the crater formed billions of years ago. Preserving that ancient surface while working within it may prove almost as demanding as extracting the frozen treasure hidden beneath. Most places on the moon offer at least one familiar point of reference. Look upward, and Earth usually hangs in the sky as a constant companion, larger and brighter than our moon appears from home. For generations of astronauts, that distant blue world provided more than a navigational landmark. It remained a visible reminder that home was never entirely out of sight. Shackleton's floor offers no such reassurance. Descend deep enough into the crater, and Earth disappears completely. The surrounding walls rise roughly 14,000 feet above the basin, enclosing the interior with an unbroken ring of towering rock. Near the lunar South Pole, Earth remains relatively low above the horizon. From the crater floor, the rim blocks that view entirely, leaving no direct line of sight toward our planet. That geometry creates an immediate engineering challenge. Radio signals travel in straight lines, just as light does. Once a rover or crew moves beneath the rim, direct communication with Earth is interrupted. Every message, command, scientific measurement, and status report must find another path if it is to leave the crater. One solution lies far beyond the moon itself. Engineers can position communication spacecraft in a halo orbit around the Earth Moon's second Lagrange point, a special region where the combined gravitational influence of Earth and the Moon allows a spacecraft to follow a stable looping path while maintaining favorable views of both worlds. From there, signals can be received from the lunar South Pole and forwarded back toward Earth, bridging a gap that the crater walls would otherwise make impossible. Another important element of that network is the planned lunar gateway. Rather than circling the moon in a simple circular orbit, it is designed to occupy a near rectilinear halo orbit, an elongated path that repeatedly carries the station close to the lunar South Pole before swinging much farther away. During favorable portions of that orbit, Lunar Gateway can serve as a communication relay supporting exploration around Shackleton. Yet it will not remain directly overhead at all times, requiring additional relay systems to ensure dependable coverage. Even with those technologies in place, distance introduces unavoidable delay. Radio signals require an average of approximately 1 3/10 seconds to travel one way between Earth and the Moon. That brief interval may seem insignificant, yet it prevents truly immediate control of robotic equipment. When communication must also pass through orbiting relay spacecraft, operating machinery inside the crater becomes an exercise in careful planning rather than instant reaction. For people working there, another consequence is harder to measure. Apollo astronauts often spoke about seeing Earth above the lunar horizon, describing it as a powerful reminder of connection with everyone they had ever known. On Shackleton's floor, that familiar point of reference vanishes behind stone walls. No sunrise brightens the landscape. No blue globe hangs overhead. Every conversation with home depends upon machines beyond the crater, each link in the communication chain becoming as essential to survival as air, water, or power in one of the most isolated workplaces humanity has ever contemplated. Imagine beginning the design of a rover by removing one assumption that has guided nearly every planetary mission. There will be no dependable sunlight to recharge batteries. There will be no warm afternoon to help frozen components recover. Every system must function in an environment where darkness and intense cold remain constant from arrival until departure. Most robotic explorers sent to the moon or Mars have relied upon either solar panels or radioisotope thermoelectric generators. A radioisotope thermoelectric generator produces electricity by converting heat released during the natural decay of radioactive material, most commonly plutonium 238. Both approaches have proven reliable across decades of exploration, yet Shackleton forces engineers to reconsider how each performs under conditions unlike any previously encountered. Solar power presents the simplest problem. It cannot operate where sunlight never reaches. A panel capable of supplying abundant electricity elsewhere on the moon becomes little more than extra weight once it descends beneath Shackleton's rim. Every watt required for driving, drilling, communication, and scientific instruments must therefore come from another source. Radioisotope thermoelectric generators appear better suited, although they introduce their own complications. Their continuous heat output usually protects spacecraft from freezing, but inside an environment approaching negative 413 degrees Fahrenheit, managing that heat becomes an intricate balancing act. Too little warmth allows sensitive electronics to fail. Too much concentrated heat near frozen deposits could alter the surrounding environment that scientists hope to study in its original condition. Energy storage presents an equally difficult obstacle. Lithium ion batteries, the standard power source for many modern spacecraft and electric vehicles, perform poorly as temperatures fall. Below roughly negative 40 degrees Fahrenheit, their available capacity declines dramatically. Near the conditions expected on Shackleton's floor, conventional battery chemistry effectively stops functioning. A fully charged battery could become almost unusable unless kept within a carefully controlled thermal enclosure. The mechanical systems face similar challenges. Metals, polymers, lubricants, and flexible seals all respond differently under intense cold. Materials that perform flawlessly elsewhere may become brittle after prolonged exposure. Every wheel, bearing, cable, and joint must also contend with electrostatically charged lunar dust seeking every exposed surface. Even routine movement becomes an exercise in preventing abrasion, contamination, and mechanical seizure. To overcome these problems, engineers have begun developing warm electronics boxes, heavily insulated compartments that maintain computers, batteries, and critical control systems within their safe operating temperatures. Small radioisotope heaters provide a steady source of warmth inside these protective enclosures. The concept works well in theory, yet every additional layer of insulation and every heating system increases the rover's weight while reducing the payload available for scientific instruments. The National Aeronautics and Space Administration's Volatiles Investigating Polar Exploration rover represents one of the most advanced attempts to explore the lunar South Pole. Designed to investigate regions near permanently shadowed terrain, it incorporates technologies specifically intended for polar conditions. Even so, it is not expected to descend into Shackleton's deepest interior. That distinction illustrates the scale of the challenge. Building a rover capable of operating on Shackleton's floor for even a single day would require solving problems involving power, temperature, materials, mobility, and contamination all at once. Few places in the solar system demand so many engineering breakthroughs before the first wheel ever touches the ground. More than half a century has passed since human footprints were last pressed into lunar soil. On December 14th, 1972, the crew of Apollo 17 departed the moon, concluding an extraordinary era of exploration. For decades afterward, no astronauts returned. Robotic spacecraft continued expanding our knowledge, yet the dream of people working regularly on the lunar surface remained suspended between ambition and reality. That long interval defines the importance of the Artemis program. Rather than repeating the achievements of Apollo, it seeks to establish a new pattern of exploration built around longer stays, more capable technology, and the gradual development of a lasting presence beyond Earth. As our understanding of the lunar South Pole has grown, Shackleton has become one of the places shaping those plans. The first major step came with Artemis 1, launched on November 16th, 2022. The Space Launch System rocket carried the uncrewed Orion spacecraft on a journey around the Moon before returning safely to Earth after approximately 25 and one half days. The mission demonstrated that the launch vehicle, spacecraft, and supporting systems could complete the demanding voyage through deep space without astronauts aboard. The next planned mission, Artemis 2, is intended to carry 4 crew members on a lunar flyby without landing. It will mark the first human journey beyond low Earth orbit since Apollo 17, allowing engineers and mission planners to evaluate Orion's life support systems, navigation, and crew operations during an actual voyage around the Moon. Attention then turns toward Artemis 3. Current plans call for astronauts to land near the lunar South Pole, within roughly 4 miles of Shackleton's rim. That location was selected because it combines scientific opportunity with access to terrain unlike any explored during the Apollo era. From there, astronauts may investigate permanently shadowed regions that have preserved ancient frozen material for billions of years. Supporting that mission is an entirely different class of lunar lander. The Human Landing System is planned to be Space Exploration Technologies Corporation's Starship, a spacecraft dramatically larger than the landers used during Apollo. Its greater carrying capacity allows more equipment, expanded scientific capability, and longer operations on the surface than earlier generations could support. Mission planners expect Artemis astronauts to remain on the Moon for approximately 6.5 days. That exceeds the surface duration achieved by Apollo 17, whose crew spent a little more than 3 days conducting geological exploration. The additional time opens opportunities for more detailed fieldwork, careful sampling, and the deliberate testing of technologies intended for repeated use. Among the highest scientific priorities is the direct examination of material collected from permanently shadowed regions near Shackleton. For the first time, astronauts are expected to gather samples from terrain that has remained beyond human reach since the crater formed. Those specimens may preserve an exceptionally old record of the Moon's history and the delivery of water throughout the inner solar system. Perhaps the greatest difference between Apollo and Artemis lies in their purpose. Apollo demonstrated that humanity could reach the Moon. Artemis is being designed to learn how humanity might remain there, transforming exploration from a series of remarkable visits into the beginning of a sustained presence shaped by the unique opportunities surrounding Shackleton. Finding water inside Shackleton answers only the first question. A far more difficult one follows immediately afterward. How do you transform ancient frozen material into something people can actually use without destroying the remarkable record preserved inside it? The difference between discovery and survival depends upon that answer. The deposits scattered across the crater floor are far more complicated than a sheet of clean ice. Scientists expect the frozen material to be mixed with regolith, the layer of fragmented rock and dust covering the Moon. Billions of years of cosmic radiation have also altered its upper layers through countless chemical reactions. Mixed among the water may be frozen methane, carbon dioxide, sulfur-bearing compounds, and other volatile materials preserved alongside the ice since the earliest history of the solar system. One proposed solution is known as thermal mining. Instead of digging out large blocks of frozen ground, engineers would gently heat the surrounding regolith using electrical heaters or carefully directed mirrors positioned where sunlight remains available. As the temperature rises, the water does not melt into liquid. It undergoes sublimation. the process in which solid ice changes directly into water vapor without passing through a liquid state. That vapor could then be captured inside specially cooled chambers, where it would condense and be collected for later use. The method sounds elegant, yet it carries an important scientific cost. Heat introduced into deposits that have remained unchanged for billions of years could permanently alter delicate chemical layers, recording the history of impacts, comet deliveries, and radiation exposure. Every degree of warming risks modifying information that cannot be recreated once disturbed. Engineers, therefore, face a careful balance between harvesting resources and preserving one of the most valuable geological archives on the Moon. Another approach relies on mechanical excavation. Robotic machinery would scoop frozen regolith from the crater floor and transport it to a separate processing facility positioned some distance away. There, controlled heating could extract water under carefully monitored conditions. This strategy reduces the chance of losing vapor directly into the surrounding environment, although it demands powerful excavation equipment capable of functioning through extreme cold, abrasive dust, and continuous operation. Regardless of how the water is obtained, additional processing becomes essential. Dust particles, chemically altered compounds, and radiation produced contaminants must all be removed before the water becomes suitable for drinking or for industrial use. Fuel production requires especially high purity because even small impurities can interfere with equipment designed to separate water into hydrogen and oxygen through electrolysis, the process of using electricity to split water into its constituent gases. Providing enough energy for that entire chain of operations presents another obstacle. A meaningful refueling outpost would require continuous electrical power far beyond what present-day rover systems can realistically generate. Many researchers, therefore, expect that a compact nuclear fission reactor will eventually become necessary. The National Aeronautics and Space Administration's Fission Surface Power Project is developing exactly that kind of system, with a design goal of producing approximately 10 kilowatts of uninterrupted electricity. It represents the first practical step toward transforming frozen lunar resources into the essentials of exploration, allowing science and survival to become parts of the same carefully engineered system. The destination attracting the greatest attention is no longer a broad stretch of the lunar surface. Instead, interest has narrowed toward a small region surrounding the Moon's south pole, where multiple nations and commercial partners now direct their plans. What was once an isolated scientific curiosity has become the center of an international effort shaped by exploration, technology, and the promise of resources that could support future missions far beyond the Moon itself. Among the most important recent milestones came on August 23, 2023. India's Chandrayaan-3 mission achieved the first successful landing near the lunar South Pole, touching down at approximately 69 degrees south latitude. Although the landing site lay roughly 370 miles from Shackleton, the achievement demonstrated that precision operations within the challenging polar environment had become possible, opening a new chapter in lunar exploration. Only days earlier, events had unfolded very differently for another mission. Russia's Luna 25 spacecraft attempted its own journey toward the South Polar region, but crashed into the Moon on August 19, 2023, after an orbital maneuver failed. The loss represented a major setback for Roscosmos and illustrated how demanding polar missions remain, even for nations with long histories of lunar exploration. China has pursued a steadily expanding program of its own, The Chang'e missions have already accomplished several historic firsts, including the first successful landing on the moon's far side and the return of lunar samples from the near side. Looking ahead, Chang'e 7 is planned to explore the South Pole using an orbiter, a lander, a rover, and an especially intriguing addition, a compact flying probe designed to hop into permanently shadowed craters that wheeled vehicles cannot easily reach. That flying probe may become one of the first machines capable of directly sampling material preserved inside one of these permanently shadowed regions. By briefly entering terrain inaccessible to conventional landers, it could gather information about frozen deposits that have remained largely untouched since the earliest stages of lunar history. Such measurements would complement orbital observations with direct examination of material hidden beneath the crater rims. As scientific ambitions increase, legal questions become increasingly important. The Outer Space Treaty of 1967 established that no nation may claim sovereignty over the Moon or any other celestial body. Yet the agreement says remarkably little about extracting natural resources. It prohibits ownership of the Moon itself, while leaving uncertainty over how materials removed from its surface should be governed. One attempt to clarify those questions is the Artemis Accords, a set of principles developed to guide peaceful exploration and the responsible use of lunar resources. More than 30 nations had joined the Accords by 2024. China and Russia have chosen not to participate, leaving different groups of spacefaring nations operating under different legal interpretations as exploration advances. For billions of years, Shackleton existed beyond human attention, shaped only by impacts, radiation, and the slow passage of cosmic time. Today, its value is measured in science, engineering, and opportunity. The decisions made there may influence not only who studies the moon first, but also how humanity chooses to share resources on worlds that belong to no single nation. Imagine holding a history book that was never written with ink. Instead, every page is a layer of frost deposited across immense stretches of time, each preserving a different chapter from the earliest days of the solar system. That possibility has transformed Shackleton from a promising source of water into one of the most valuable scientific archives known beyond Earth. The frozen material, gathered inside the crater, almost certainly did not arrive during a single event. Over billions of years, countless processes contributed to its growth. Comets striking the moon delivered water and other volatile compounds. Asteroid impacts added their own material. The solar wind, a continuous stream of charged particles flowing outward from the sun, interacted with oxygen bound inside lunar minerals, creating additional water molecules. Some researchers also suggest that ancient volcanic activity may have released gases from the moon's interior, allowing small amounts of water to migrate toward the permanently frozen polar regions. If those deposits formed gradually instead of mixing together, the ice may exist in distinct layers. Orbital observations have hinted that such layering is possible, although confirming it will require direct sampling. Each preserved layer would correspond to a different period in solar system history, protected for immense spans of time by temperatures approaching negative 413 degrees Fahrenheit. Under those conditions, chemical reactions proceed extraordinarily slowly, allowing ancient material to remain remarkably well preserved. Within those frozen layers may rest samples from comets that crossed the inner solar system billions of years before telescopes, spacecraft, or even Earth itself possessed oceans filled with life. Rather than studying modern comets as they pass through the solar system today, Scientists could examine the actual material left behind by ancient visitors whose original forms disappeared long ago. Some researchers have proposed an even more remarkable possibility. Portions of Shackleton's water may be older than the liquid oceans covering our own planet. Earth's surface has been reshaped continuously by plate tectonics, erosion, and the cycling of water between land, sea, and atmosphere. The moon lacks those active processes. Frozen deposits, trapped inside permanent darkness, may therefore preserve water that has remained largely undisturbed since before Earth's oceans reached their present form. The chemistry within that ice could help answer one of planetary science's oldest questions. Hydrogen exists in different forms, including ordinary hydrogen and deuterium, a heavier isotope containing an additional neutron. By measuring the ratio between these forms, scientists can identify whether the water originated primarily from comets, asteroids, or interactions between the solar wind and lunar minerals. If Shackleton's isotopic signature closely resembles that of Earth's oceans, it would strengthen the idea that impacts delivered much of our planet's water during its earliest history. The ice may also preserve organic molecules, carbon based compounds that serve as essential ingredients for life on Earth. Their presence would offer an extraordinary glimpse into the chemical environment from which planets and living systems eventually emerged. Yet every scoop of frozen soil removed for fuel or drinking water also risks erasing part of that record forever. Shackleton presents an extraordinary dilemma. The very resource that could sustain future explorers is preserved within one of the most scientifically irreplaceable archives humanity has ever discovered. Beneath every landscape lies another story, one that cannot be seen from orbit or photographed by a passing spacecraft. Shackleton's frozen surface has already revealed remarkable possibilities, yet the rock below may conceal an entirely different kind of treasure. If we could somehow look through hundreds or even thousands of feet of lunar crust, we might discover that the crater is only the uppermost layer of a much larger underground world. One possibility involves lava tubes, natural tunnels created during the moon's volcanic past. They formed when flowing lava cooled and hardened along its outer surface, while molten rock continued moving through the interior. Eventually, the eruption ended, the remaining lava drained away, and an empty passage was left behind. What remained was not a cave carved by water, but a vast corridor built by ancient rivers of molten stone. Evidence that these tunnels exist is no longer speculative. Orbital spacecraft have identified collapsed openings known as skylights, where portions of a lava tube roof have fallen inward, exposing the hollow passage below. These features provide direct evidence that enormous underground cavities survive beneath parts of the lunar surface after billions of years. Some researchers estimate that the largest lunar lava tubes could approach 2/3 of a mile in width, while extending for hundreds of miles through ancient volcanic terrain. Their immense size results from the moon's lower gravity, which allows broad ceilings to remain structurally stable far more easily than similar formations on Earth. Inside one of these passages, an entire city could theoretically fit beneath a single continuous arch of solid rock. The lunar South Pole was not the center of the moon's most recent volcanic activity. Those younger volcanic plains are concentrated much closer to the familiar face of the moon visible from Earth. Even so, the southern polar region is ancient enough that older lava tubes may still exist beneath its surface, buried beneath countless impacts and hidden from every spacecraft that has passed overhead. If such a tunnel were discovered beneath or near Shackleton, its significance would extend far beyond geology. Imagine a naturally shielded underground habitat positioned below one of the richest known reservoirs of lunar ice. Thick layers of rock overhead would reduce exposure to cosmic radiation and micrometeorite impacts. Temperatures deep within the passage would also remain comparatively stable, perhaps hovering between roughly -4 and -22 degrees Fahrenheit, regardless of the severe conditions above. Confirming the existence of such a structure remains extraordinarily difficult. Scientists would need seismic instruments capable of detecting vibrations traveling through the crust or ground penetrating radar, a technique that sends radio waves into the subsurface and measures the returning reflections to reveal hidden structures. Neither approach has yet been deployed on Shackleton's floor, leaving this possibility unresolved. For now, the idea remains one of the moon's great unanswered questions. Yet, if a future expedition uncovered an ancient lava tube beneath Shackleton, explorers would gain something far more valuable than another geological curiosity. They would discover a place where natural shelter and accessible resources exist together, a combination unlike any other location yet identified beyond Earth, and one capable of reshaping every future plan for living and working on the moon. Before the first step is taken, the greatest challenge may already exist inside the human mind. Every astronaut who has explored another world has carried familiar points of reference into that experience. During the Apollo missions, sunlight illuminated the landscape. Earth remained visible overhead, a brilliant blue destination suspended against the darkness of space. Those constant visual cues linked every moment on the moon with the world waiting beyond it. Shackleton's floor removes nearly all of those anchors at once. Descending beneath the crater rim leaves Earth hidden from view. The surrounding walls dominate every direction, replacing the distant horizon with towering slopes of ancient rock. Looking upward reveals only a narrow opening to space rather than the broad lunar sky experienced elsewhere. You remain on the moon, yet your surroundings resemble an enclosed world with almost no familiar landmarks. Above that confined landscape stretches an extraordinary view of the universe. Without an atmosphere to scatter light, the stars appear as precise points across the darkness. They never shimmer or flicker. Thousands remain visible at the same time, while the Milky Way extends overhead as a dense river of distant suns. No city lights compete with that view. No air softens its clarity. From Shackleton's floor, humanity could witness perhaps the clearest natural night sky ever seen from a permanent outpost beyond Earth. Another change is harder to describe because it involves something we rarely notice until it disappears. Air carries every ordinary sound on Earth, from footsteps to distant weather. The moon has no atmosphere, so those vibrations cannot travel between objects. Inside Shackleton, the surrounding terrain further isolates the environment from distant activity elsewhere on the surface. Outside a spacesuit, the landscape offers an almost complete absence of naturally transmitted sound, leaving only vibrations conducted through equipment and the constant operation of life support systems reaching the astronauts' ears. Time itself may gradually lose its familiar rhythm. There is no sunrise marking morning. There is no sunset announcing evening. Earth never climbs above the crater wall or slips below the horizon. Without those repeating patterns, the human brain must rely almost entirely upon clocks and scheduled routines rather than natural cycles that have guided our species throughout its history. Researchers have explored similar psychological questions in Antarctica, where crews spending the polar winter experience months without daylight. Studies conducted during those expeditions have documented changes in sleep patterns, mood, concentration, and cognitive performance despite extensive preparation and support. Shackleton would present many of the same challenges, while adding greater physical isolation and a far harsher environment. The first explorers reaching the crater floor will move inside bulky spacesuits that restrict natural motion. Every conversation with Earth will depend upon relay spacecraft. Scientific instruments must continue operating in temperatures approaching negative 413 degrees Fahrenheit. Even the strongest headlamps illuminate only a small portion of the surrounding darkness. In measurable ways, those astronauts will occupy the most isolated workplace humanity has ever attempted, separated from home by distance, hidden from direct view, and surrounded by a landscape unlike any experienced by previous generations of explorers. A single step can separate two environments that seem as though they belong to different worlds. Along the inner rim of Shackleton, the boundary between lasting shadow and brilliant sunlight forms one of the sharpest natural transitions known anywhere in the solar system. Standing there, you would occupy a place where two radically different physical realities meet across only a short walking distance. The change in temperature is astonishing. A traveler moving from the permanently shaded interior toward ground exposed to direct sunlight could cross a difference exceeding 540 degrees Fahrenheit in only a brief walk. Few natural environments anywhere experience such an abrupt horizontal contrast. Instead of changing gradually across seasons or landscapes, the moon compresses that enormous thermal shift into a remarkably narrow zone. Rock responds to those extremes in ways that continue shaping the crater today. Minerals expand when heated and contract as they cool. Along Shackleton's boundary, this repeated cycle places tremendous stress upon the surrounding stone over billions of years. Tiny fractures widen, larger cracks eventually develop. Pieces of the crater wall may loosen and collapse as the accumulated strain slowly weakens the ancient structure. Scientists believe this process contributes to the complex geology of the inner slopes, although many details remain uncertain because no mission has yet examined these cliffs directly. Yet the boundary offers advantages alongside its hazards. Complete darkness ends surprisingly abruptly. Although sunlight never reaches the permanently shadowed interior itself, light reflected from the illuminated rim can scatter into the upper edge of the darkness. This indirect glow is extremely faint compared with ordinary daylight, but sensitive instruments positioned near the transition may receive enough illumination to supplement electrical power generated by solar panels under carefully planned conditions. Engineers within the European Space Agency have explored a concept known as International Graduate Laboratory for Utilities and Nuclear Application, often shortened to IGLUNA. The proposal imagines a habitat located near the shadow boundary rather than deep within the crater. Such a position could provide relatively convenient access to resources preserved below while maintaining proximity to regions where sunlight is available for power generation and surface operations. Although originally developed as a research and training initiative, the concept reflects a broader strategy for balancing engineering practicality with scientific opportunity. The boundary also functions as an active transport system. Molecules released from warmer terrain by thermal stress or other surface processes can drift across the airless lunar environment until they encounter intensely cold regions. There, they become trapped within the frozen deposits. This gradual migration means Shackleton continues receiving new material even today. Rather than preserving only an ancient record, the crater remains connected to ongoing processes occurring across the surrounding moon. When humans eventually arrive, their first footsteps are expected to touch this remarkable dividing line before descending farther inward. There, beneath an unchanging sky, They will stand at the meeting place between enduring sunlight and enduring darkness, between warmth and extreme cold, between familiar engineering challenges and one of the least explored environments humanity has ever approached. That narrow boundary may become one of the most carefully studied landscapes on the moon, precisely because it joins two extraordinary worlds without belonging entirely to either one. Long before anyone imagined extracting water from the moon, another possibility remained almost hidden within the data itself. The frozen deposits preserved inside polar craters may contain far more than ice. They may preserve an inventory of ancient chemistry assembled over billions of years, with each newly identified molecule adding another clue to the environment from which the planets eventually emerged. A turning point arrived during the National Aeronautics and Space Administration's Lunar Crater Observation and Sensing Satellite mission in 2009. After deliberately impacting Cabeus Crater near the lunar South Pole, the spacecraft analyzed the plume of material blasted into space. Scientists expected to find water, and they did. They also found something far richer. Mixed into the ejecta were carbon monoxide, carbon dioxide, methane, ethylene, ethanol, ammonia, and hydrogen sulfide, revealing that the permanently shadowed regions preserve a surprisingly diverse collection of volatile compounds. Shackleton has not yet been sampled directly in the same way, but orbital observations indicate that its geological setting closely resembles other permanently shadowed craters. If those similarities extend beneath the surface, the frozen deposits there may represent far more than a reservoir of water. They could preserve a chemical library, assembled from countless impacts, solar interactions, and ancient processes spanning nearly the entire history of the solar system. Among the most intriguing compounds is ammonia. This simple molecule contains nitrogen, an element essential for living systems on Earth. Many planetary scientists believe at least some lunar ammonia arrived aboard comets originating beyond Neptune in the distant Kuiper Belt, a vast ring of icy bodies orbiting beyond the outermost major planets. The Kuiper Belt is a region filled with frozen remnants left over from the formation of the solar system, preserving material that has changed very little for billions of years. Discovering such compounds inside Shackleton would mean that pieces of that distant frontier eventually reached the moon and remained preserved there. Carbon-bearing compounds also carry remarkable practical value. Future explorers could potentially process them into useful industrial materials rather than launching every required supply from Earth. Carbon-based feedstocks offer pathways toward manufacturing plastics, specialized lubricants, and structural materials needed for long-duration operations. Nitrogen extracted from frozen volatiles has likewise attracted attention because enclosed habitats require breathable atmospheres containing more than oxygen alone. Even limited local supplies could reduce dependence upon cargo launched across space. Perhaps the most surprising discovery from the Cabeus plume was ethanol. Its presence does not suggest that life ever existed on the moon. Instead, it demonstrates that natural chemical reactions operating throughout the early solar system were capable of producing biologically relevant organic molecules long before living organisms appeared. Those reactions unfolded inside comets, icy dust grains, and primitive bodies moving through space, creating increasingly complex chemistry from simple ingredients. If Shackleton preserves the same molecular diversity, its frozen layers may contain one of the most complete chemical records available anywhere beyond Earth. Within those ancient deposits could rest a remarkably intact snapshot of the raw materials from which planets, oceans, atmospheres, and eventually life itself were assembled, preserved across billions of years beneath one of the coldest landscapes in the solar system. Names sometimes become more than labels. They become reminders of the people whose lives reshaped our understanding of what exploration demands. Every time scientists refer to Shackleton Crater, they also recall Ernest Shackleton, the explorer whose determination became one of history's defining examples of endurance under impossible conditions. Ernest Shackleton led the Imperial Trans-Antarctic Expedition between 1914 and 1916 with the ambitious goal of crossing Antarctica. The journey changed completely when his ship, Endurance, became trapped within expanding sea ice. As the pressure increased, the wooden vessel was eventually crushed beyond recovery. Instead of abandoning hope, Shackleton reorganized the expedition around survival itself. He guided all 27 members of his crew across drifting ice, through one of the roughest stretches of the Southern Ocean in a small lifeboat, and over unmapped glaciated mountains after reaching South Georgia Island. Against extraordinary odds, every member of the expedition returned home alive. That history gives unusual meaning to the crater carrying his name. Although Ernest Shackleton never imagined astronauts descending into a permanently shadowed lunar basin, the challenges associated with that place reflect many of the qualities that defined his expedition. Extreme cold, prolonged isolation, limited resources, and the need for careful judgment unite these two frontiers, despite the immense distance separating Antarctica from the Moon. Planners within the National Aeronautics and Space Administration have often recognized those similarities while preparing for future lunar missions. Antarctica provides one of Earth's closest natural comparisons to the lunar South Pole, because both environments require long-duration operations far from immediate assistance. Equipment failures become serious problems. Every supply must be carefully managed. Success depends as much upon teamwork and preparation as advanced technology. One of the most valuable research locations for these studies is Concordia Station, operated jointly by the European Space Agency and Italy upon the Antarctic Plateau. During winter, the station experiences continuous darkness for months, while temperatures can fall to approximately negative 112 degrees Fahrenheit. Medical researchers have used these isolated crews to study sleep, cognition, teamwork, and the psychological effects of prolonged separation from the wider world. Many of those findings now help shape preparations for future expeditions beyond Earth. Even the word pole carries shared meaning across both worlds. On Earth and on the Moon alike, the poles are defined by the geometry of a rotating sphere and its relationship to the sunday. At these extreme latitudes, sunlight remains low above the horizon, producing landscapes where shadow becomes a dominant feature of the environment rather than a temporary visitor. When the first explorers finally descend toward Shackleton, they will arrive wearing sophisticated spacesuits, supported by spacecraft, computers, and the efforts of millions of people whose work made the journey possible. Yet beneath all that remarkable technology lies an ancient human instinct that has changed very little across history. From the earliest travelers crossing unfamiliar continents to Ernest Shackleton steering a small lifeboat through freezing seas, to the Apollo astronauts leaving footprints on another world, the same enduring curiosity continues leading us outward toward places where knowledge waits beyond the edge of what is already known. Every great voyage depends upon a place where supplies can be gathered before the journey continues. Across Earth's oceans, ports transformed exploration by allowing ships to replenish food, water, and equipment instead of carrying every necessity from the beginning. Shackleton may eventually serve a remarkably similar purpose, except its harbor would stand on the moon rather than beside an ocean. The frozen deposits preserved within the crater are valuable for reasons extending far beyond lunar exploration itself. Water can sustain human crews, but it can also become rocket propellant after electrolysis separates it into hydrogen and oxygen. Those two elements, when cooled into liquid form, produce one of the most effective chemical fuel combinations ever developed for spaceflight. Every gallon of water recovered from the lunar surface therefore represents more than life support. It represents stored transportation. This idea is known as in-space refueling, the practice of replenishing spacecraft with fuel after launch, instead of requiring every mission to leave Earth carrying its complete supply from the start. The concept changes how engineers think about exploration. Rather than lifting enormous quantities of propellant through Earth's powerful gravity, spacecraft could depart carrying only enough fuel for the first stage of their journey, then replenish their tanks using resources obtained beyond Earth. That difference becomes increasingly important when planning expeditions to Mars. A direct voyage from Earth typically requires approximately 8 to 9 months of travel under favorable orbital conditions. If a spacecraft could refuel after reaching the lunar South Pole, mission planners would gain greater flexibility. The same launch from Earth could deliver a heavier scientific payload, additional supplies, or larger habitation systems. Alternatively, more fuel available after departure from the moon could support trajectories that reduce overall travel time while carrying the same payload. The moon's comparatively weak gravity also transforms the energy required for launch. Escaping from the lunar surface demands only a fraction of the energy needed to leave Earth because lunar gravity is roughly 1/6 as strong. Every pound of propellant manufactured on the moon therefore becomes easier to transport into deep space than fuel launched from Earth's surface. Economic studies have reached striking conclusions about this possibility. At current launch costs, a single kilogram of lunar water converted into rocket propellant has been estimated to possess a value approaching $100,000 once available in space. That figure reflects the tremendous expense of lifting equivalent material from Earth and explains why lunar resource extraction has attracted growing commercial interest. Several private companies, including Astrobotic, Intuitive Machines, and iSpace, are already developing lunar landers and robotic prospecting vehicles intended to support this emerging economy. Their efforts complement government exploration programs while testing technologies that may eventually support routine operations around the lunar South Pole. Seen from that broader perspective, Shackleton becomes something larger than a destination. It becomes infrastructure, a propellant depot supplied by resources extracted there could serve spacecraft traveling toward Mars, the asteroid belt, and even the distant outer solar system. The crater formed during a violent impact billions of years ago may ultimately become one of the most economically important locations beyond Earth, not because explorers choose to remain there, but because it enables them to continue farther into the solar system. Some places enter human history all at once. Others reveal themselves through decades of careful progress, each expedition solving only one part of a much larger puzzle. Shackleton belongs to the second kind. Although its promise has become increasingly clear, reaching the crater in a meaningful way depends upon a sequence of missions that must build upon one another with patience rather than speed. Current planning within the National Aeronautics and Space Administration continues to place the first crewed return to the lunar South Polar region in the later years of this decade. although that schedule has shifted several times as spacecraft, landers, and supporting systems have matured. Exact launch dates remain uncertain because every stage depends upon successful testing and the readiness of multiple vehicles working together. Human exploration of the moon has always required flexibility as much as ambition. Before astronauts venture close to Shackleton, robotic explorers are expected to gather the detailed measurements that orbiting spacecraft cannot provide. One of the most important planned missions is the Volatiles Investigating Polar Exploration Rover. Designed to examine the composition and distribution of frozen deposits near the crater's rim, the rover would provide direct measurements of lunar soil, helping scientists compare orbital observations with conditions on the ground. That process is often called ground truth, meaning information collected directly at the location rather than inferred from a distance. Another important effort comes from China's planned Chang'e 7 mission. Its mission design includes a hopping probe capable of descending into a permanently shadowed region where conventional wheeled vehicles would struggle to operate. By briefly entering one of these frozen environments and analyzing material there, the mission could provide valuable insight into conditions that have remained largely inaccessible since the moon formed. If current momentum continues, the first human excursion to the edge of Shackleton's shadow could occur during the closing years of this decade or the early years of the next. Reaching the crater floor itself presents a much greater engineering challenge. Hardware capable of surviving temperatures approaching negative 413 degrees Fahrenheit while maintaining reliable communications and power has not yet been fully demonstrated under real lunar conditions. Developing those systems will likely require additional years of testing. Extracting useful quantities of water represents another major milestone. Small scientific samples may come first, but producing enough water to support sustained operations demands mining equipment, processing facilities, storage systems, and dependable energy sources working together as a single integrated network. Under even optimistic projections, that level of capability belongs more naturally to the decade after the first human visits. Longer term planning extends still farther. Many studies envision a permanent South Polar base operating during the middle of this century, where ongoing ice extraction supports life support systems and produces propellant for spacecraft departing the moon. You can imagine that future as one continuous chain rather than a single dramatic achievement. Every rover, every lander, every crew, and every experiment contributes another link. Shackleton is therefore less a destination with one arrival date than a generational undertaking, advancing step by step until the coldest known crater on the moon becomes part of humanity's lasting presence beyond Earth. Some discoveries become valuable precisely because they have remained untouched for unimaginable spans of time. Shackleton's frozen deposits belong to that rare category. Their remarkable state of preservation depends upon an environment that has changed very little for billions of years. Once human activity begins inside that delicate system, the balance maintaining those ancient layers may never be exactly the same again. The ice survives because temperatures remain extraordinarily low and sunlight never reaches the crater floor. Under those conditions, molecules arriving from comets, asteroids, or the surrounding lunar surface become trapped instead of escaping back into space. That process has continued across immense stretches of time, building an archive one microscopic layer after another. Altering even the uppermost surface could erase information that accumulated over hundreds of millions of years. A single rocket engine operating near the crater floor illustrates the challenge. Its exhaust would release heat, expanding gases, and fine particles into an environment that has experienced almost none of those disturbances throughout its preserved history. Surface ice could transform directly into vapor through sublimation, the process in which frozen material changes into gas without first becoming liquid. Once those molecules disperse or relocate, their original arrangement cannot be reconstructed. Heat represents only part of the concern. Rocket exhaust also contains water vapor, carbon dioxide, and traces of unburned hydrocarbons. In Shackleton's extreme cold, many of those compounds would freeze almost immediately after settling onto the surface. Future researchers examining those deposits might then encounter a mixture of natural material and substances introduced by human exploration, making it more difficult to distinguish the original chemical history preserved within the crater. These concerns have led to ongoing discussions surrounding planetary protection protocols. The internationally recognized guidelines intended to reduce harmful biological and chemical contamination during the exploration of other worlds. Although the moon is not treated identically to locations where life might exist, permanently shadowed regions have received increasing attention because of their unique scientific importance and the possibility that early missions could permanently alter environments that cannot be restored. Scientists remain divided over the best path forward. Many argue that the resources preserved inside Shackleton are too valuable to leave unused when they could support exploration across the solar system. Others believe extensive scientific investigation should come first, even if that careful characterization requires many years before industrial activity begins. Their concern centers upon preserving the original record before irreversible changes occur. Accidents also remain part of every realistic exploration plan. A crashed lander or a malfunctioning rover, unable to control its internal heat, could expose nearby ice to temperatures far above its natural state. The resulting chemical changes might affect only a limited area, yet even that small region could contain an uninterrupted record extending across billions of years of solar system history. Unlike many damaged environments on Earth, Shackleton offers no practical method of restoration once disturbance has occurred. The first successful landing on its floor, no matter how carefully executed, will leave a permanent signature behind. For that reason, deciding how and when to explore this remarkable crater reaches beyond engineering, economics, or technology alone. It asks humanity to determine how we should treat one of the oldest and most pristine natural archives ever discovered beyond our own world. You know darkness from experience. Evening arrives, temperatures shift, city lights appear, and eventually the sun returns. Even the deepest cave remains connected to a world where daylight still exists beyond its entrance. Our understanding of darkness has always been shaped by the expectation that it is temporary, a condition waiting for illumination. Shackleton introduces an entirely different idea. The darkness covering its floor is not a passing event. It is a permanent consequence of the moon's shape, the crater's towering walls, and the remarkably small tilt of the lunar axis. Those simple geometric relationships have combined across billions of years to prevent direct sunlight from reaching the basin below. No season arrives to change the outcome. No annual cycle shifts the sun high enough above the horizon. The geometry simply endures. That distinction changes everything. Here, darkness is not merely the absence of light. It becomes a physical environment with measurable consequences. Temperatures remain extraordinarily low because solar energy never enters to warm the surface. Volatile molecules remain trapped because frozen material rarely gains enough heat to escape. Every scientific characteristic discussed throughout this journey begins with that single, persistent condition. Even observing the crater from orbit reveals how unusual this environment truly is. Conventional cameras depend upon reflected sunlight to record landscapes beneath them. Over Shackleton's floor, there is essentially no direct sunlight available to reflect. Some of the clearest orbital images have instead relied upon Earthshine, the faint illumination created when sunlight reflects from Earth's cloud tops and oceans toward the moon. That delicate glow is thousands of times weaker than ordinary daylight. Images gathered under those conditions required extensive processing before recognizable surface features slowly emerged from the darkness. Imagine standing there yourself. Your eyes would gradually adapt, as they always do after entering a dark room, reaching the limits of human night vision. Yet, adaptation would accomplish almost nothing because there would be virtually no incoming light for your retinas to detect. Without artificial illumination attached to your suit or equipment, the landscape around you would remain visually inaccessible. Human vision cannot create information where no photons arrive. This remarkable absence has become one of Shackleton's greatest scientific strengths. The preserved ice, ancient volatile compounds, and chemical record discussed earlier survived precisely because sunlight never interrupted the crater's thermal stability. Warmth would have erased much of that history long ago. Instead, the permanent shadow protected it with extraordinary consistency across geological time. Many of the moon's greatest challenges arise from what it lacks rather than what it contains. Shackleton offers almost no natural warmth, almost no natural illumination, and almost no visual reference for an arriving explorer. Yet those very absences have protected one of the oldest archives in the inner solar system. As we have followed the story of this remarkable crater, its defining lesson becomes increasingly clear. Sometimes the most valuable place is shaped less by the presence of extraordinary things than by the enduring absence that allowed those extraordinary things to survive across billions of years. For as long as people have gathered beneath the open sky, the moon has watched over every generation. It has accompanied ancient migrations, guided sailors across unfamiliar seas, marked calendars, inspired stories, and shared the night with every civilization that has ever existed. You inherit that same relationship. The moon feels familiar precisely because no human life has ever unfolded without it. Yet familiarity can conceal astonishing mysteries. Only within the last few decades have we learned that our nearest celestial neighbor contains places no human eye has ever directly observed from the surface, landscapes hidden by geometry rather than distance. Among them rests Shackleton, a crater preserved in conditions so extreme that ordinary earthly experience offers almost no comparison. Its existence reminds us that even the object most consistently present in our skies has kept profound secrets. That realization reshapes the moon itself. Instead of appearing as a smooth companion hanging above Earth, it becomes a genuine world with mountains, valleys, ancient lava plains, towering rims, and regions that have remained beyond direct human reach throughout the entire history of our species. Shackleton is one remarkable example, yet it also represents something broader. The closer we examine familiar worlds, the more complexity they reveal. Its age deepens that perspective. Shackleton already existed before the first fish ventured onto land. It remained unchanged while forests spread across continents, while the dinosaurs appeared and disappeared, and while mammals gradually diversified into forms that eventually included us. Long before the earliest humans looked upward and wondered about the bright disk crossing the night, this crater had already completed most of its history. The frozen material preserved upon its floor is equally ancient. Much of that ice likely accumulated when the young solar system still contained abundant icy debris crossing the paths of the inner planets. Water delivered during those distant eras became trapped beneath permanent shadow while Earth continued transforming through volcanoes, oceans, changing continents, and evolving life. Across all that time, the crater simply endured, preserving evidence from an age when our own planet was still settling into the world we recognize today. One day, a person may stand along Shackleton's rim and direct artificial light into that immense darkness for the first time. Looking downward, they will see more than rock and ice. Before them will rest a preserved record whose timescale reduces the entirety of recorded human civilization to a remarkably brief interval. Empires, languages, inventions, and written history together occupy only the smallest fraction of the story contained within that landscape. The crater itself remains indifferent. Whether people arrive or remain forever absent changes nothing about its natural existence. The cold will persist, according to physics. The preserved ice will continue responding only to energy, temperature, and time. Darkness will remain until human technology introduces light where none has naturally reached. Our decision to journey there, therefore, carries meaning beyond exploration alone. Choosing to enter that ancient place declares that knowledge possesses lasting value, that even the oldest untouched corners of a familiar world deserve our attention, and that home is not merely where humanity began, but also every place where curiosity, responsibility, and understanding eventually choose to meet. A single crater on the moon can seem like an isolated curiosity until we recognize the pattern it represents. Once you understand why Shackleton exists, similar places begin to appear throughout the solar system. Different worlds, different histories, and different environments all arrive at remarkably similar destinations whenever lasting shadow and intense cold endure together across immense spans of time. Mercury offers one of the most surprising examples. As the closest planet to the Sun, its sunlit surface becomes hot enough to melt many metals. Yet near its poles, deep craters never receive direct sunlight. Observations by the National Aeronautics and Space Administration's Mercury Surface, Space E-Environment, Geochemistry, and Ranging spacecraft confirmed during 2012 demonstrated that these permanently shadowed regions contain substantial deposits of water ice. The same physical rules operating inside Shackleton continue working even beside the brightest star in our planetary neighborhood. The pattern extends farther outward. Ceres, the largest body within the asteroid belt and officially classified as a dwarf planet, also possesses permanently shadowed craters where bright deposits are consistent with exposed water ice. Although Ceres occupies a completely different environment from either Mercury or the Moon, its sheltered depressions preserve frozen material through the same fundamental balance between limited sunlight and persistent cold. More distant worlds reveal additional variations on this theme. Charon, the largest moon orbiting Pluto, possesses a permanently dark northern polar region known as Mordor Macula. Instead of bright ice, this landscape displays a deep reddish coloration produced by substances called tholins. Tholins are complex organic molecules created when simple gases and frozen compounds are altered by energetic radiation across billions of years. They demonstrate how prolonged exposure to space can gradually transform basic ingredients into increasingly complex chemistry, offering another example of time acting upon preserved material. The great moons of the outer planets continue the story from different directions. Europa hides an immense ocean beneath an icy shell. Enceladus ejects water vapor through fractures, reaching its buried sea. Titan supports lakes and rivers composed primarily of liquid hydrocarbons, while water exists as rock hard ice. Although these environments differ dramatically from Shackleton, they all demonstrate the same broad principle. Wherever water or volatile compounds remain protected from conditions that would rapidly remove or destroy them, they can persist for extraordinary lengths of time. That lesson may reach far beyond our own solar system. Rocky planets, orbiting distant stars, almost certainly possess mountains, valleys, and impact craters shaped by the same laws of gravity and orbital motion. Where favorable geometry creates permanent shadow, there is no known physical reason preventing similar cold traps from preserving water and complex chemistry across billions of years. Those hidden locations could become the richest molecular archives within their planetary systems. Viewed from that wider perspective, Shackleton no longer appears unusual. Instead, it becomes an example of a universal process unfolding wherever darkness, cold, and time meet without interruption. Physics patiently gathers fragile molecules, protects them from destructive energy, and preserves them until some future intelligence arrives with curiosity enough to understand what has been waiting there all along. Every great expedition eventually reaches a point where calculations alone are no longer enough. The engines have been designed, the trajectories refined, the materials tested, and the risks carefully measured. Then another question quietly emerges within the planning process. Why should anyone make this journey at all? That question cannot be answered by engineering alone. It belongs equally to science, history, and the human desire to understand our place in a universe that existed long before we arrived. Shackleton has remained in darkness for roughly 2 billion years. The universe itself has spent almost all of its existence in a similar condition. Across approximately 13.8 billion years of cosmic history, stars have been remarkable interruptions rather than the ordinary state of reality. They flare into existence, shine for immense yet finite lifetimes, and eventually fade. Between them stretches a cosmos that is overwhelmingly cold, dark, and astonishingly vast. You and I exist because of one of those interruptions. Our sun gathered dust, ignited nuclear fusion, and provided the steady energy that allowed oceans, chemistry, and eventually living organisms to flourish on Earth. Every breath, every thought, and every question traces its origin to that continuing source of light. Yet beyond its influence remain places where the older conditions of the solar system still endure with extraordinary fidelity. The frozen water resting within Shackleton may share an ancient ancestry with the water that helped shape our own planet. Many scientists conclude that icy comets and water-rich asteroids contributed part of Earth's inventory of water during the early history of the solar system. Some of those same deliveries reached the moon, while Earth's surface transformed through geology, weather, and life. Portions of that lunar water remained preserved beneath permanent shadow, waiting through ages almost impossible to imagine. Traveling to Shackleton, therefore, carries an unexpected sense of returning rather than merely advancing. We would be approaching materials that existed before forests, before animals, before continents reached their modern arrangement, and before any living creature possessed eyes capable of looking toward the moon. The destination lies only a journey of several days from Earth, yet the history preserved there reaches farther into the past than any civilization, language, or species. Eventually, explorers may descend into that ancient crater, extract water, transform it into fuel, and use those resources to continue outward across the solar system. If that day arrives, Shackleton's story will not conclude. It will simply enter a new chapter in which preserved materials from an ancient darkness help carry humanity toward worlds even farther from home. The crater presents no hostility born of intention. Its dangers arise from indifference. Cold follows the laws of physics. Darkness obeys geometry. Time continues without preference for success or failure. Those realities remind us how brief our lives truly are. Yet they also extend an extraordinary invitation. By accepting the challenge of understanding places like Shackleton, we acknowledge that curiosity can bridge the distance between a fragile civilization beneath one star and a universe whose oldest stories have been waiting, unchanged, for someone to read them.